everyone. Good afternoon, good morning, good evening. Welcome to today's Science Talk. I am delighted to welcome you. For those of you joining us for the first time, we're delighted to have you with us. My name is Dr. Miriam Axel, and I'm pleased to be hosting this talk. We'd like to remind you that you can watch the entire 2024 series as well as the 2025 series on our website and on our YouTube channel. Our website is unu.edu/INWEH/science-talks with an S at the end. Today's talk, like all of our others, will be recorded, and we will share the recording after the session. We'll also conclude with an interactive Q&A session, so please put your questions in the Q&A box and I will share them with our speaker. Don't wait until the last minute. Feel free to put questions in at any point during the talk and I will make sure to read them out. Today's talk is titled Material Needs for Power-to-X Technologies, Environmental Life Cycle Assessment, LCA, and Social Life Cycle Assessment, SLCA. And I'm delighted and honored to introduce today's speaker, Professor Salim H. Ali, who's the lead Critical Minerals and Inclusive Energy Transition here at UNU-INWEH. Professor Ali is an environmental security scholar whose research focuses on resolving ecological conflicts and fostering peace between corporations, governments, and communities. And at UNU-INWEH, he leads cutting-edge research on critical minerals for a green, just, and inclusive energy transition. He's the author of several books, including Soil to Foil, Aluminum and the Quest for Industrial Sustainability, Earthly Order, How Natural Laws Define Human Life, Treasures of the Earth, Need, Greed, and a Sustainable Future, Environmental Diplomacy, Islam and Education, Conflict and Conformity in Pakistan's Madrasas, and numerous other anthologies. Salim has worked in over 160 countries and is a National Geographic Explorer and World Economic Forum Young Global Leader. He also serves on the boards of Resolve, Adventure Scientists, and Mediators Beyond Borders International. Professor Ali holds degrees from MIT, Yale, and Tufts, and is the Blue and Gold Distinguished Professor at the University of Delaware and a member of the United Nations International Resource Panel. And now, without further ado, it's my great honor to turn it over to you, Professor Ali.
Thank you so much, Dr. Axel, for the generous introduction. Great to connect with colleagues at UNU and beyond. The presentation that I'm giving today, it's the first time I'm presenting it anywhere. It's brand new research that we've been undertaking through one of my other affiliations, which is in Australia. And that is through the Australian Research Council Centre of Excellence on the Green Electrochemical Transformation of Carbon Dioxide. That is a mouthful, but we have a nice acronym, which is GET CO2. So if you are interested in further information on this center, which is a $25 million enterprise funded by the Australian government over 7 years, you can go to the website. It's getco2.org, and it's based at the University of Queensland in Brisbane. It's a real pleasure to work on this center for me personally because it connects many of my various academic interests. My first degree was actually in chemistry, and that in some ways is where a lot of my passion comes from around materials. Because as a chemist, you have to be concerned about the elements of the earth. You have to be anchored in the periodic table. And so a lot of my later work, where I moved more towards the social sciences, was still informed by that passion for chemistry. But for a long time, I wasn't really able to get back into, fundamental chemical research. And most of my work has been around environmental and social conflicts around mining, extractive industries. And even though I'm looking at minerals from the point of extraction and that kind of research, I often don't end up going deeper into the chemistry of all of the processing and so on. Now, this center has provided me an opportunity to reconnect with chemists and chemical engineers And the first paper that has come out of this center's work in this space that I've been involved in was just published 2 months ago, and this is what I'm presenting to you. And the paper's reference is given there. It was published in the journal Chemical Science, which is published by the Royal Society of Chemistry in the UK. And it's what we call a Diamond Star journal. Diamond Star meaning that it's free to publish in, open source both ways. So you don't have to pay a publishing fee to be open source, and it's always open source, which is really great. So anyone in the developing world with really appropriate for UNU audiences, they can access the article for free online, and people who want to publish in that journal from the developing world can also publish for free, unlike some of these other open source journals where you have to pay large publication fees. So those of you who want to connect on social media also, my contacts are there, whether it is through X or Threads or LinkedIn, it seems is the most likely place where professionals like to connect, but you can find me there. So let's move on then, Miriam, to understanding what are power to X systems. So this term power to X, it has its origins in Germany, where researchers started to think about what can be done with surplus energy that comes out of certain renewable energy production. And certainly with hydropower, that's the most widespread area. There was potential to use the excess energy to have like storage of that. Kinetic energy can be converted to potential energy, and then it can be stored in like pumped hydro facilities and things like that. Or you could have batteries which could store the charge. But then the third area was what we are referring to here as power to X, is where that excess energy then can be used in real time to make chemicals, and those chemicals then can be used in various production processes and manufacturing. So this is what is referred to as power to X. The most common example of power to X now is green hydrogen production, where you have the excess power from these renewable energy technologies, and it could be solar and wind also, that during times when you don't need it. I mean, one of the things with electricity is once it's produced, it's flowing, and you can't just stop it. You have to either store it, you have to do something with it, right? That's like a physical property of electricity. So the electrons can't just be stopped like that. You have to then figure out either a storage mechanism or some other way of harnessing and using it. So one of the things that we have been, the most commonly been proposing for power to X is to use that renewable energy then for electrolysis to make hydrogen, and then using hydrogen for fuel or for whatever other production manufacturing processes we use. So the most common use of power to X has been in hydrogen, in green hydrogen particularly. And for those of you who study hydrogen, there are many different forms of hydrogen. Green hydrogen, as the name suggests, is the most sustainable approach because you are using renewable energy to produce the hydrogen. But there's also what we refer to as blue hydrogen, where you could have some of the other way to produce hydrogen is through natural gas, and there are chemical processes whereby you can use methane and take out hydrogen from the methane molecule. And that, of course, then requires you to use a non-renewable resource. And also there's a danger of fugitive emissions and so on. And so that is less preferable to this. If you then sequester any kind of carbon impacts, then that is considered blue hydrogen. If you don't, then there's what we call gray hydrogen. You can use nuclear energy to make the electrolysis. That's called pink hydrogen. So you have all these shades of hydrogen. We're talking about the green hydrogen. That's where a lot of the power to X technology is focused. Okay, so let's move on then to the next slide, Miriam, which is giving you an idea of, so next slide, sorry. Okay. The next slide is showing us what the center in Australia is focused on is specifically electrolyzers, not for hydrogen, but for carbon dioxide production. Okay. And so you are using that energy then for, instead of synthesizing hydrogen, which is the usual power to X, you are using the renewable energy from these sources to convert carbon dioxide into useful materials and sources. So this is different from carbon capture and storage. In carbon capture and storage, you are taking the carbon dioxide and putting it in geological deposits, and you are able to store it for extended periods of time. And that would be a way by which you mitigate carbon emissions. But in the case of CO2 conversion through electrolyzers, you are converting the carbon dioxide into chemicals, which can then be used. So this is very important as a potential way for us to deal with the emissions challenge if we are not able to mitigate directly. And for a long time, there was resistance to these technologies because there was what we call the moral hazard problem. And the moral hazard problem being that there was this concern that people would somehow not be incentivized to curtail their emissions if we gave them a solution. Right? There was this constant fear that if we provide a solution, then people will not want to reduce emissions. And for a long time, this has been the conversation in the climate community, that they've resisted these kinds of technical solutions. They've also resisted adaptation solutions for a long time because of this moral hazard problem. Until very recently, you may know that over 90% of climate finance went to mitigation rather than adaptation. But that is now beginning to change because we are realizing the danger of tipping points and the fact that we are unfortunately not meeting those targets that need to be set before we reach those tipping points. So these technologies are going to become more important because of this reality that humanity is not being able to mitigate emissions. And this is, from a sustainability perspective, also attractive because you are putting that carbon dioxide to some productive use. And you're making chemicals which we might otherwise need anyhow. And so that's the goal of these electrolyzers. So next slide, Miriam. So what is an electrolyzer? An electrolyzer, first of all, people confuse fuel cells and electrolyzers. We often hear about like hydrogen fuel cells. I told you about the fact that we use power to X for hydrogen production. In some ways, fuel cells, electrolyzers, you can say, are two sides of the same coin. They both utilize electrochemical processes, but with slightly different functions. Fuel cells, they will convert chemical energy into electricity, while electrolyzers convert electricity into chemical energy. Okay, so in the case of a full, like a hydrogen economy, you need both. You need fuel cells and electrolyzers, right? It depends on what you are doing at what stage of the process. Okay. So electrolyzers produce hydrogen from water using electricity, but then that hydrogen, if you are going to uh, be using that to generate electricity later, you will need a fuel cell to do it. Okay. So in the case of hydrogen, you need both. For carbon dioxide, we are only focused on using the electrolyzer technology because we are not going to be using the CO2 itself. First of all, we have the CO2 already. So in the case of hydrogen, you first have to produce the hydrogen, then you have to use it as fuel. In the case of carbon dioxide, we have excess carbon dioxide, and you are not going to be using it for fuel anyhow. The products that you are going to use are going to be chemicals which are not going to be burned, because that would defeat the purpose. If you burn them, you again produce carbon dioxide. They will hopefully be chemicals which will be used for other purposes. And those could be organic chemicals in various ways that could be used. In some cases, the end goal is to also think about how they could be converted into ammonia and fertilizer production with nitrogen conversion and all. That is beyond the scope of our talk here, but there's a really interesting array of research that is happening on what would be part of the way in which that carbon dioxide manufacturing supply chain would then be used for. There are people who are, talking about, different kind of artificial photosynthesis, even food generation from some of these. One of our colleagues at the ARC Center, Feng Jiao, who is also affiliated with Washington University and is a co-author on this paper, has been supported by the Gates Foundation to look at some of those aspects. So it's a fascinating new area of research, and we have just started. The center is just a little over a year old, and we have 6 more years to go. All right. So that's what electrolyzers are. Now, the goal of this paper was to do a reality check on this new technology and say, wait a minute, we've got this great technology, but what will we need to make this work in the long term if we upscale it? A lot of my work as an environmental planner is around trying to look at the full systems issues that surround our embracing of new technologies. And so I try to dig deep, quite literally, into the supply chain of these new technologies and understand what will we need to make them work at the larger scale. Because in the euphoria of developing these technologies, sometimes we forget the material reality behind them. Okay, we saw this many years ago with catalytic converters, where it was a great technology, but the materials we need a lot of platinum to make them work. There were a technology to control pollution in cars, but we had to really upscale platinum production. Luckily, we had South Africa as a huge producer of platinum, and so they were able to provide that. But if we had not had that, we would have not been able to upscale that technology. So that's what we are trying to do in this paper, is to say, look, let's look at all the materials that are needed from a systems perspective, and also see what are the sources of those materials, what will be the impacts environmentally of their extraction, both environmentally and socially. And then we make a decision on what kind of technology is best and how to upscale it. Okay, so we make informed systems level decisions. And that's the kind of work I think UNU is very well positioned to do, because UNU has all these institutes that have different areas of expertise. And this kind of an approach can bring them all together to consider the different aspects of what we call life cycle analysis, which is a methodology used to study the impacts comparatively of different kinds of outputs. The classic life cycle analysis, paper versus plastic, what kind of, whether we should use fiber optics cables versus copper cables, and you can go down the supply chain. What are the different ways in which you harness, silica sands for fiber optics versus copper mining? What's the relative environmental impact? And you can quantify them. And now there are software packages which help us to actually do these analyses. Life cycle analysis is a very advanced field. There are even ISO standards on doing life cycle analysis. So this has been a mature field for past 20 years or so. So what we are suggesting in this paper is let's look at this technology. Let's see what are the materials we need and then use a life cycle approach. In the paper, we don't do a life cycle analysis because that's a very complicated process and it takes a lot of resources to do. But we suggest that it can be done and we provide the inventory of the kinds of materials and the sources that need to be considered to do the LCA. Okay, next slide. All right, so this diagram is giving you the different ways in which these electrolyzers are working. And here we've given three examples. There's the hydrogen electrolyzers, carbon dioxide electrolyzers, and the nitrogen electrolyzers. And they're telling you essentially what happens in the full circuit in terms of these different kinds of flows. For the carbon dioxide itself, you need to capture it either from the air directly, what we call direct air capture, or if you have a point emission source, you can certainly get it from that point source at the smokestack and then channel it through to the electrolyzer process and so on. The direct air capture is very costly, very difficult to do. There are only a few facilities now in Iceland, the most notable one where they're doing direct air capture. But the point source emission is certainly very plausible and easy to do and should be considered. So essentially, that then goes into the electrolyzer, and that's what we are interested in. It's that box, the rectangle in the center, which we are interested in. All the three electrolyzer technologies require very similar materials. One of the arguments we make in the paper is that we need to think about also how these electrolyzer technologies will be competing with each other. The hydrogen one is the most mature, and if we need the CO2 electrolyzers also, it will require us to be competing for materials with the hydrogen market as well. And then the nitrogen electrolyzers, certainly in terms of the use of nitrogen for fertilizers, it's very significant in terms of how that will play out. And we also know that fertilizer production is extremely energy intensive as well with the Haber-Bosch process and so on. So, from a systems perspective, we have to think about all of these interactions. Next slide. So this is how these electrolyzers they work. They work with essentially a kind of a different approach with membranes and different forms of metals and organic materials that are placed next to each other. And then you have, of course, the electrodes as well. And these are highly specific in terms of how they are put together. And these are just examples of two of these kinds of technologies. And I don't have to go into the acronyms for this, but essentially, you can see that there is this complexity of these layers of materials and the membranes. And a lot of the patented and proprietary kind of aspects of this are the materials used in the membranes and these plates that provide just the right cost curve as well as the right efficiency in order to be able to harness the chemical energy that you want, and then convert also the CO2 into those useful products that you will be able to get at an efficient output. Okay, so here you can see, for example, you have nickel is noted, those symbols, yttrium, there are different chemical formula which are put forward there, but just for your reference, you can see that it is very complex, and the anode and the cathode, these are close proximity to each other with these different alloys that are put together like a sandwich in between. That's what they look like physically. Next slide. Now, from the point of view of where these chemicals are and where these metals are particularly that we are using, these are the ones which we have inventoried that are needed for the electrolyzers. So you've got iridium that is a very rare metal. As you know, iridium is one that often we use as an example of a metal that is linked to meteorites. And even the impact of the asteroid that destroyed the dinosaurs is measured through this layer of iridium that is found in geological deposits. Now, you need a lot of iridium. In the case of some of these electrolyzers, most of it is mined as a byproduct uh, of mining the platinum group metals. And this is showing you these different countries, and the ZAF is South Africa. And you can see the other ones: China, Australia, Mexico, and so on. So the metals that we need are, some of them are pretty exotic. Platinum, palladium are okay still, though they are fairly rare and highly concentrated in a few locations. Nickel is manageable. Titanium is widely used, of course, in aerospace industries. And incidentally, among the metals that President Trump has been negotiating with Ukraine on, the most mature metal mines that Ukraine has, in fact, are the titanium mines. The rare earth mines are not really developed, much as the media likes to talk about the rare earth metals there. It's the titanium really where Ukraine is well developed. You have copper, yttrium. Yttrium is used in small amounts, but is really important in terms of some of the catalytic activities that are needed for these electrolyzers. Zirconium, strontium, and lanthanum. Lanthanum is one of the rare earth metals. And just for those of you who are not as much into chemistry, generally speaking, rare earths we define in chemistry as those metals at the bottom of the periodic table that are separated from the main table. And we have lanthanum on the top, and then actinium, and you have the lanthanides and the actinides, we call them. So those are what generally are referred to as rare earths, but sometimes people lump together others in common parlance. But generally, the rare earths are the lanthanides. Um, so this is the challenge we have now. If you think about also this diagram, the one that is labeled D, that sorry, the label is missing for some reason when it was copied, but that is essentially showing recycling worldwide estimated recycling rates. So, people will ask me then often, well, can't we just recycle? We don't have to mine them. The challenge with recycling these metals for production is that you have what we call the durability paradox, that if you are going to have durable infrastructure, which is what we want these electrolyzers to last a long time, then you don't have them available for recycling stock. So if you have growth in demand, then you have no ability to recycle them. You have to mine them then, right? So recycling presents this paradox. It's a good thing, but it comes at the sacrifice of being durable, which is the ultimate goal of any sustainability outcome, right? You want things to be durable unless the technology changes where things become more efficient. Otherwise, you want things to last a long time. So that's the big problem. But you can see here the recycling rates for a lot of these is really low. Gold is really high, but we don't need gold that much. And gold for these particular electrolyzers, but gold has very high recycling rate because it is so modular and is so readily available in terms of ingots and jewelry and so on. But the others you can see not that good. Even platinum, which should be very easily recyclable because catalytic converters are the largest users of platinum currently, and they are essentially available in cars. When a car is returned or sold or goes to the junkyard, it should be fairly straightforward to get the catalytic converters out. But still, we have only 45% for platinum and a little bit higher for palladium. Um, so this is the dynamic we are looking at in terms of these electrolyzers, and we have to be very conscious of then the next steps that we need to take to move this idea forward. Next slide. So here we have just tried to analyze the demand intensity, the supply side scarcity, and the price volatility all together in this kind of color-coded, more qualitative comparison. And the ones which we are most worried about are iridium and nickel. Iridium, I've already talked about. So let's talk a little bit about nickel. Um, Nickel right now is becoming increasingly significant for a variety of reasons. And that is historically, it was used largely for steel production, for certain kinds of steel. But nickel is also very important in a range of batteries. Most battery technologies require nickel. And we have this real conundrum around where to mine nickel, because the largest deposits of nickel now, which are potentially viable to extract, are actually in the deep sea. And so there has been this big controversy about whether we should be mining nickel from these polymetallic nodules in the deep sea. And you've probably been hearing all the news around this, including the recent executive order from the US government just last week, which has authorized the Bureau of Ocean Energy Management and the National Oceanographic and Atmospheric Administration to start expediting exploration licenses for deep sea mining, even in international waters, which is currently under the United Nations Convention on the Law of the Sea and the International Seabed Authority. So nickel is going to be really interesting to follow. The largest source of terrestrial nickel, and currently the largest producer of terrestrial nickel, is Indonesia. But we also have very large nickel reserves in Russia and Canada. Of course, keep in mind that this in not far from where UNU-INWEH is in Sudbury, Ontario, you had historically the world's largest nickel deposits. But a lot of that nickel has been depleted. Incidentally, that the Sudbury deposits of nickel, they go back to a meteor impact that happened in Sudbury about 1 billion years ago. And that is what led to the deposit of so many metals in Sudbury. So it was, again, a celestial kind of incident that led to that. And then New Caledonia in the Pacific, which is a French overseas territory, that also has massive nickel deposits. So this is going to be really interesting. If these technologies get upscaled, they will be competing for nickel with all of these other places as well. Copper, we have very high demand intensity, but we are not as worried about the supply side because it does come from a variety of sources still. The other ones are manageable, except platinum, still concerned about it. Yttrium, even though it's a rare earth, because it's used in very small amounts, we've kept it at that medium range in terms of how it's going to be potentially impacted by this. So if these technologies, the electrolyzers for carbon dioxide conversion, are going to be upscaled to the point where industries are using these to make useful chemicals at large scale, you will see a massive demand increase. Our next step in our research is to estimate that based on what is realistic. So do scenario analysis around this and see what would happen down the road with this kind of technology being upscaled. So finally, last slide, the life cycle analysis approach that we are suggesting in this is that we essentially, as the term suggests, life cycle analysis, you go from cradle to cradle, what used to be called cradle to grave. You go from where the material is starting and can you go back to the same starting point through the whole life cycle of the material, which would be ideal? And you try to minimize as much of the disposal as possible. But at each step, there will be impacts, and you measure those impacts. If you don't design the product well, you will have impacts at the point of extraction, disassembly, remanufacturing, all of those points, and you have to be conscious of measuring them. On the social side, you will also have major impact. So, for example, with Indonesia, I gave you the example of the nickel mining in Indonesia. That is happening in a relatively remote part of the country, in an area near Sulawesi. There are a few remote islands near Sulawesi and on Sulawesi itself. That whole region, that ecosystem is known as the Coral Triangle, one of the highest biodiversity ecosystems in the world. And the water impact, particularly of nickel processing, where they have a technique called submarine tailings disposal, where the processed waste of the mining is dumped directly into the ocean. That is going to be very significant. So if you're doing an LCA, you compare that damage and potential impact to other sources of the metal. For example, the deep sea. And that is also research I have done. Actually, I have written a paper with colleagues doing an actual LCA, which compares the nickel that's mined from terrestrial sources and the nickel that's mined from the deep sea, if we were to mine it, and sees what are the different comparisons. So when it comes to, if we just look at the waste issues, and this was published in Journal of Industrial Ecology about 3 years ago, the waste from the deep sea mining is much less because those polymetallic nodules are highly concentrated in metal. So when you process them, you don't end up producing as much waste. So from a waste perspective, the LCA comes out favorable for deep sea mining compared to terrestrial mining. But then you could look at biodiversity impact, and biodiversity is more subjective. It's very difficult to say because people who study the deep sea, they will say, well, there are all these microbes that are there which are unique, and we need to pay attention to their specificities. And in the case of the Coral Triangle, of course, you have a lot of amazing marine macrobiodiversity, which is going to be significant. So that one is a little bit trickier. You just lay it out and present what are the different parameters there. You could do an LCA on carbon footprint and compare the relative carbon impacts of the two kinds of nickel. On the social side too, you would look at how would you do a social life cycle analysis? A social life cycle analysis would look at livelihoods, how many jobs are created, but also how many jobs might be lost. It could look at how lifestyles would change. Would people have to be resettled, as has happened with many mines? One of the advantages of also mining in remote areas is that you may not have to resettle people, even though there may be biodiversity impact. So there's a trade-off between the social and the biodiversity side. So that's how, from a systems analytic point of view, then you come up with the analysis, and then it's policymakers who have to decide what kind of data do we want to use to make those decisions? What weighting do we give to these different factors? That will always be a value-based decision. But our role as scientists is to make sure we inform that with as accurate data as possible on impacts. So it's not just wishy-washy and biased information based on anecdotes. That's the goal of the LCA approach. And with any new technology, this is something which I feel very strongly about. We have to advocate. We have been advocating within the United Nations International Resource Panel. Some of our main work is around material flows and ensuring that we apply industrial ecology approaches like life cycle analysis for policy evaluation. And I would urge those of you within the UN community, the IRP publishes the Global Resources Outlook every 3 years. We spend a lot of time into these reports, and we are constantly coming up with new products. So please visit also the Resource Panel website, which is resourcepanel.org, which will give you some ideas on how some of these kinds of analytics can be done, and how science-based targets can then be set, which is something the Earth Commission has also been trying to do, and the IRP has been sharpening that focus specifically on the resource dimension of that. And then just to finally wrap up, I should put in a plug for the fantastic work Miriam is helping me with, and she has led already an existing report on artificial intelligence with UNU. But we are hoping to do some future work looking at the material needs for artificial intelligence technologies, which no one has looked at. People have focused on energy, that AI will use a lot of energy. But the material side is far more complex and potentially more perilous in terms of supply constraints. And whether it is AI servers or transmission infrastructure, and the speed with which AI technology is being upscaled is unprecedented in terms of any kind of upscaling of computational technologies. So this is going to be extremely important to watch and make sure we are able to track and see what happens. And this should require us to make tough decisions on what kind of use AI should be put to. Because, like, for example, I was telling my students, we should not be using AI just like we do a Google search, because you require far more computational energy to do a search on ChatGPT compared to just a simple Google search. And that requires also then potentially, if you have too much load, you will end up having to use more materials to build servers to relieve the load so people don't get stuck with very slow processing speeds. So we need to be really conscious of these decisions, of these technologies that we feel so euphoric about. So with that, I'll stop, and we have about 15 minutes for Q&A. Thank you.
Oh, thank you so much, Professor Ali. That was really interesting. Let's see these. Yeah, I did stop share.
Close.
All right. Thank you. I'm so glad that you brought up AI. I wonder if maybe you could talk a little bit about how AI could be used to better understand or better model these potential trade-offs that you talked about with power to X technologies. You know, where might they be truly beneficial and where might they have greater life cycle impacts?
Yes, so I mean, I think where AI can be really helpful is optimization kind of algorithms that could be used for figuring out um, energy pathways and how to make the energy usage more efficient itself originally, so that if you're using renewable energies to different sources of renewable energy to make these different products, what would be the best optimization timing of how the energy is used. So just like with smart grids, you know, AI can be very effective for that. That's operationally speaking. The other thing that AI can be used for is like figuring out what's the best kind of material that can be developed, like the membranes which are developed. You need certain molecular forms. And this is where the Nobel Prize for AI last year in chemistry that went to AlphaFold and Dennis Hassabis and colleagues was more at the molecular level how AI can be used to find the right kind of molecules that we need for these membranes and these materials. And because, in the old days, chemists would try different things and they would have some hypothesis on why one chemical would work better than others. But the real power of AI is it can help you run those experiments much more efficiently without actually even getting your hands wet, because it has that amazing ability. And that's been the great revolution of what AlphaFold was able to accomplish with protein synthesis. So similarly, you could apply AI to all these other different kinds of molecules that you need for the membranes, the materials. So that could be a really useful way to have AI put to use, certainly.
And then we have a couple of questions in the Q&A box. So Dr. Abu Shomar says, considering that water electrolysis is central to power to X systems, what are the implications for freshwater availability and quality, especially in water-stressed regions? Are there sustainable strategies, such as using wastewater or seawater, being explored that can reduce competition with drinking water supplies?
Yes, absolutely. So this would be for the hydrogen electrolysis, production, the production of hydrogen from electrolysis through the electrolyzers, not as much for the CO2, because that's where it would be utilized the most. Most of it is, being done in coastal areas is where it's suggested. So you can do it in those kinds of settings where you can use. I mean, it is tricky with completely wastewater. There can be problems with the electrolysis if you do just wastewater, but it can be done with seawater in certain situations. So I think there shouldn't be too much of concern about drinking water per se, because drinking water is a very relatively small usage of water. The biggest issue is the agricultural water usage, but I would say it's something to keep an eye on. Certainly, if you are concerned about inland production of hydrogen, and you're using groundwater or you're using fresh water from the surface in inland areas. But for coastal areas, I think it can be done fairly well.
Thank you. And another question is, how do we guard against power to X being used as a license to continue emitting today under the assumption that we'll clean it up later? And I guess maybe an extension on that, how do we ensure that there isn't a physical rebound as well, in, sort of dealing with a Jevons paradox type issue
Yeah.
where the increasing efficiency leads to greater emissions?
Yeah. Well, I mean, I think, this is a behavioral issue of whether how much do we feel we can change behavior. If we live in a liberal society, there are limits to what we can do to change behavior. We can regulate up to a certain point. But if behavior doesn't change beyond that with those, then you need to be able to plan for these kinds of approaches to ensure that you can still meet your targets, right? And it's important to have these options. It's like people saying, well, smoking causes cancer, but it doesn't mean that if you can't stop all people from smoking, that you don't find a cure for cancer, right? You still have to do both, because there are limits to what we can do to stop people from smoking. So I think that kind of is, in some ways, I find that after a certain point, those arguments, the moral hazard arguments, can become a bit stagnant and they're not very productive. You still need to try and find solutions because there are limits to what you can do to change behavior. As far as Jevons paradox is concerned, the issue with rebound around energy efficiency issue. I mean, the rebound part is, of course, with any kind of efficiency issue. I always say, even with circular economy, with recycling, you have to be concerned about rebound, right? That's why I am very keen on keeping track of aggregate consumption. We should always try to reduce aggregate consumption. whether it's plastics or any kinds of materials. So the IRP's work, we have always focused on keeping an eye on what is the total consumption output, because that is important. So I'm not by in any way saying we shouldn't keep an eye on that. Um, but there will be with even with that, if we are not able to maintain that, then we need to be able to still have some other off ramps for solutions.
In terms of, you mentioned before the resources necessary to go through a life cycle assessment, and I wonder if maybe you could just walk us through a little bit what the process of doing a life cycle assessment, why it's so resource intensive, and how in practice you would go about combining the social life cycle assessment and trade-offs with the life cycle assessment for policy
Yes.
intervention.
Yes, LCA is very intensive because you are trying to look at environmental impacts at every aspect of the supply chain, and it depends what level of resolution you want. And with social impacts, it can become more qualitatively intensive. If people want to do interviews, ask people, how will this change? If you're starting a new nickel smelting plant and you want to do a social LCA, ideally you want to have some data on how people's lives will change. How do they feel their perceptions of quality of life will change. Now, some of that is what we call subjective well-being. Some of it is objective well-being. You can look at objective well-being like, indicators of health, indicators of income. Those are those data you can use, but some people feel we still need subjective well-being criteria as well. So that becomes more expensive. On the environmental side, water quality impacts, air quality impacts, all of those, just getting that information, projecting it, comparing it between those other sources, it's extremely time consuming to be able to do that. And so that's why they have developed these kind of software packages and all, where they can say, okay, if there's this much of this particular pollutant, then this is the threshold over which it will have a certain impact, and so on and so forth. So that helps a little bit with that. But their entire consulting firms who just work on doing LCAs as a result of those. And the LCAs, the methodologies need to be very transparent because the devil is in the detail, and LCAs can be misused. And a lot of times people obfuscate with numbers. So that is why ISO has these standards, the ISO 14000 series of standards on how you do LCA and make sure you do it well. So that's kind of why it's so complicated.
Yeah. Following up on that, Khalid, has it been done? Has a piloted case been done? And if it has there been a cost-benefit analysis on, for instance, the cost of a sizable production, and the cost-benefit analysis of the impact, the sustainability impact, environmental impact, to weigh all that together in terms of, okay, I go ahead with it in terms of cost, and the consequences, if I go ahead, has any of such been done? And if so, what are your thoughts on that?
The LCAs on electrolyzers have not been done, but on the technologies, because it's such a new technology and we are very early days into it. But we have done the LCA on the comparing nickel, manganese, and copper from deep sea mining versus terrestrial mining. We did 3 different kinds of LCAs. One was on the carbon footprint, one was on the waste, and one was on biodiversity. Biodiversity was much more subjective and not quantitative. The other 2 were quantitative. And similarly, you have LCAs have been done for different kinds of manufactured products. One example is like the new aircraft that we have, they are using carbon fibers rather than using metal. So the new, like the Airbus A350 or the Boeing 787, these are the newest generation of the wide-bodied aircraft. They're largely made of carbon fibers, but they have the chassis is metal, but the rest is carbon fibers. Before, we used to use titanium and aluminum largely for the chassis. So there have been LCAs which have compared this move. Why did the companies want carbon fibers? Because they're lighter, they save on fuel cost, right? And in some ways that helps with emissions. But from an LCA perspective, then you have to say, okay, that's one positive side. But the negative side is carbon fibers are almost impossible to recycle. What are carbon fibers made of? The feedstock of carbon fibers is petroleum. So if you do an LCA on the comparing the material that's used to make the carbon fibers, they will come out worse than the metal, even though in use the emissions will be less for the carbon fiber planes. So then you have to figure out, how many years of usage of the aircraft will compensate for that negative impact. And then hopefully you can figure out some technologies which will be able to recycle carbon fibers better, because right now they're very difficult to recycle. It's mostly downcycling. You can't, and with recycling, as you know, there are different ways. We want upcycling, but if you downcycle, it's not as useful because you can't make the same material from it. So that's an example. Those kinds of LCAs have been done.
All right, thank you.
Thank you. And I just want to go back to, I'm still sort of surprised by just how low on some of the materials that you showed, that slide that had the recyclability of them. For example, the platinum, it was quite surprising that it's so low. And I would think that that's something, I mean, I often see, I know there's sort of wishful recycling where you see in recycling things that really have a very, very little efficiency. And as somebody who's had a catalytic converter stolen off a car twice, I wish this was something that was better known, that there's this what are some of the factors that lead to such low efficiency? And is that something maybe that we need on our recycling facilities so that people have a greater awareness of the types of materials that can actually be used more easily?
Yeah, so a lot of this has to do with the diffuse aspects of the products, where they end up, and whether we have domestic capacity for collecting the scrap. So, for example, lead acid batteries, which is a much older technology, you have much higher recycling rates. For lead, the recycle, which was not on that graph because lead is not being used for these technologies. But for lead, the recycling rate's over 90% for that. For the lead acid batteries, at least lead from that, lead is used in other places. Why? Because it's an older technology. So in poorer countries as well, you have the ability to take the lead acid battery and recycle it. They don't have to send it somewhere. The catalytic converters, many times they are in the developing world, they do not have the capacity to recycle them. And there's not that awareness many times that they can be. And so they are lost in that process. Which is really unfortunate, because in fact there's a huge value that could come even to the domestic economy from recycling them, and much more so than the lead, because it's a very precious metal, as you know, from having these stolen from your car. So that those are the kinds of things which some of the work that UNIDO is doing is important in this, the United Nations Industrial Development Organization. And then recently also UNCTAD has a whole project called and I'm on the advisory board for this group called SMEP, which is on manufacturing enterprises, and especially focused on recycling of some of these areas under UNCTAD, supported by the British government. And they're focusing on developing these kinds of recycling infrastructure in developing countries so we can improve that. So there's still a lot of low-hanging fruit we could get.
Thank you. Well, unfortunately, I think we're out of time, but thank you so much for this fantastic presentation. We look forward to welcoming you in person in just a couple of days, and really
Thank you.
appreciate your time and your research.
Thank you so much. Yes, Miriam and team, all the best. Yep. Bye-bye.
Thank you.
Bye. Now I can't even log off. It's you have to log me off. My computer is just